In this video, we will be looking at the main properties of parabolas. So first of all, this is what a parabola looks like. So it's this U shape. It could also be upside down and open downwards. Now, these parabolas are formed by things called quadratic relations. So the equation of a quadratic relation is y equals ax squared plus bx plus c. And it is this x squared term that tells you that the relation is quadratic. So for a line or a linear relation, it was y equals mx plus b. All you saw was an x term. In quadratic, you have to see that x squared term. Now, parabolas can open up or down. So the one that we have in the graph opens upwards. Downwards would look something like this. Next, the y-intercept is the point on the parabola that hits the y-axis. So if we look at our diagram, this point here is our y-intercept, which we've seen when we were looking at lines. The zeros are the points on the parabola that hit the x-axis, and these are also called x-intercepts. So you will see those words used interchangeably. So these 2 points at -1 and +5 are zeros. Next, we have the vertex, and it is the tip of the parabola. So the highest or the lowest point. So in our diagram, this point here is the vertex. And the vertex results in 2 other properties. First, we have the optimal value, which is the value of the maximum or minimum. So in this example, our optimal value is a minimum of something like this, so -4.5. And it is the y-coordinate of the vertex. And then our axis of symmetry is the vertical line that cuts the parabola in half. Because a parabola has symmetry, so that axis of symmetry cuts it in half. So if we look at this line here, it passes through 2 on the x-axis. So it would have the equation of x equals 2, and it matches with the x-coordinate of the vertex. So I will label this as the axis of symmetry. So let's take these new properties. Well, some of them are new, some of them are familiar, and let's apply them to a few different parabolas. Okay, let's start with the first parabola, and let's identify the vertex. So the vertex is this point here, the tip of the parabola. So in this case, it is the lowest possible point. And the coordinate is -1, -8. So it has an x and a y value because it is a coordinate. The optimal value, so that point is the lowest possible, so it is a minimum. And the minimum, if I were to put a line across, is -8. So minimum of -8. Notice that the -8 is matching the -8 in the vertex, the same y value. And then our axis of symmetry passes through the vertex and cuts the parabola in half. And notice, as we draw that vertical line, we pass through -1 on the x-axis. So the equation is x equals -1. And notice that the -1 matches the x-coordinate of your vertex. The zeros, or the x-intercepts, are here and here. So you're looking at your x-axis and checking to see where your parabola hits it. So we do have 2. We have one at -5 and the other at 3. And because they are coordinates, we're going to write -5, 0, and the other one is 3, 0. The direction of opening, we are looking at where the hole in the parabola is, which is up here, so it opens upwards. Also, if we were to put arrows, it shows that we are going up, so that also helps with the direction of opening. And finally, we have our y-intercept. So we look at our y-axis just like with a line and see where the parabola passes through, and it looks like it's between -7 and -8. So the coordinate 0 for the x, comma, -7.5. So we have to estimate a little bit. All right, let's try the next one. So here our parabola opens up again, and let's start with the vertex. So here's the tip of the vertex. The coordinate is +1 for the x and -4 for the y, so 1, -4. The optimal value, the lowest value is still related to the vertex, and because our parabola opens upwards, we have a minimum of that -4 value. And then our axis of symmetry, this vertical line that I already started drawing, it passes through 1 on the x-axis, so it'd be x equals 1. Honestly, the minute you have your vertex, you don't even have to look at the parabola for your optimal value and the axis of symmetry, because the axis of symmetry will always match the x-coordinate and the optimal value will always match the y-coordinate. So I'll make a little note here, y, x. Okay. But visually drawing in the axis of symmetry does help remind you how to write the equation. All right, our zeros. So here is the x-axis, and my parabola passes through it at 2 different points. One of them is at -1, so I'm going to write -1, 0, because I go to -1 on the x-axis, but I don't move up or down. And then the other one is 3, 0. And this parabola also opens up. And finally, for our y-intercept, so looking at the y-axis here, my parabola passes through at this point, which is at -3. So because I'm not moving right or left on the x-axis, I am writing 0, and then -3. So for your zeros or your x-intercepts, the x will have the value and the other will be 0. For your y-intercept, the y-coordinate will be the value and x will be 0. So why don't you try to pause the video here and try the next parabola on your own, and then come back to the video to check your work. All right, so your vertex is up here, and your coordinate is 3, 4. The optimal value is the highest the parabola goes in this case. So we have a maximum of 4. The axis of symmetry, if I were to draw a vertical line, we're passing through 3. So x equals 3 because we're passing through the x-axis. My zeros, I have 1 here and here. So +1, 0. And the other one is at 5, 0. This parabola opens down, because if I were to put arrows at the ends of the parabola, they are going in the down direction. And finally, the y-intercept is right here, which is 0, -5. So if you got that, that's great. If you messed up on one of the properties, make a note of it so that you don't do that in the future. Okay, and now we have more to practice. And some of these, might be a little bit special cases in that maybe they don't have 2 zeros, or we can't see a y-intercept or something like that. So let's take a look at the next one. So the vertex here is right at the very top. and the coordinate is 0, 8. And you might notice that the vertex is actually on the y-axis, which means the vertex and the y-intercept are the exact same. So I'm actually going to fill in the y-intercept as well. Sometimes the properties overlap. The optimal value, the vertex is our highest possible value, and it is 8. So it's a maximum of 8. And in terms of the axis of symmetry, the y-axis is actually our axis of symmetry. And we're passing through 0 on the x-axis. So x equals 0. The x-intercepts, or the zeros, are symmetrical in that one of them is -2. So -2, 0, and the other is +2, 0. And this opens down again, like the previous one, because if I were to put arrows, I'm going in the down direction. Why don't you pause the video, try the next one on your own. If you made mistakes in the previous one, take a note of that and try to correct that mistake. Then come back to check your work. So our vertex is 0, -4. And this is the lowest point on our parabola, so we should have a minimum of -4. The axis of symmetry is similar to the previous example in that we're the y-axis, so we're passing through 0 on the x-axis, so x equals 0. And the zeros are actually the same as in the other example, so -2, 0 and +2, 0. This parabola does open upwards, so here are my arrows, and the y-intercept is actually the same as the vertex, so 0, -4. All right, last one. So again, pause the video, try it out, and then come back to check your work. So your vertex is right over here, which is 2, 0, 0 because you're not going up or down on the y-axis at all. This is a maximum because there is nothing above the vertex, and it's a maximum of 0. And our axis of symmetry, if I draw that vertical line, I pass through 2 on the x-axis, so x equals 2. My zeros, in all the other examples I had 2 zeros, here I only have 1, which is right here. It's actually the exact same as the vertex, so 2, 0. This parabola opens down. And finally, the y-intercept is right here, which is 0, -4. So those are some key properties of parabola, so some new terminology there. So you have to be able to look at a parabola and identify these features. So again, the vertex is the tip of the parabola, and it will result in an optimal value, so your highest or lowest possible value, and the axis of symmetry, which is that vertical line that cuts the parabola in half. We also have the zeros, which are the x-intercepts, and we have the y-intercept, which is where the parabola passes through the y-axis. And finally, direction of opening, whether your parabola is facing upwards or downwards. Now, let's look at a few linear versus quadratic properties. So when we were doing table of values for lines, we used first differences, where we subtracted the consecutive y values and we did bottom minus top each time. Now, sometimes you might see that your first differences aren't the same, they aren't constant, so we can go to second differences, which are subtracting consecutive first differences. Again, bottom minus top. So we're going to do a line example and then move on to a quadratic example to see the difference and to see a visual difference as well when we look at our table of values. So we'll start with y equals 2x minus 3. And in my table of values, I gave you x values from -2 to +2. So looking at 2x minus 3, I'm just going to replace x with the value given to me. So 2 times -2, subtract 3. And you can plug this all in your calculator, or we can do BEDMAS. So I do the multiplication first. 2 times -2 is -4. And then when I subtract 3, I get -7. And I'll plot this point. So when x is -2, y is -7. So here I am. Next, I'll do 2 times -1, subtract 3. Well, 2 times -1 is -2, and -2 subtract 3 is -5. So now I'll plot my next point. At -1, y is equal to -5. Next, we have 2 times 0, subtract 3. 2 times 0 is 0, and 0 subtract 3 is -3. So at 0, we're at -3. Next, we have 2 times 1, subtract 3. So 2 times 1 is 2. Subtract 3 is -1. So at 1, we're at -1. And finally, 2 times 2, subtract 3. 2 times 2 is 4, and 4 subtract 3 is +1. So when x equals 2, y equals 1. And then we can connect our dots and put arrows at the ends. And this is clearly linear because we have a line on our graph, but also the equation was in y equals mx plus b. Now, this whole portion is about first differences, so let's go ahead and do that. So I'm going to go to the bottom of my table, and I'm going to pair up the first set of y values. And I'm going to do the bottom, which is 1, subtract the -1. That double negative actually becomes 1 plus 1, which is 2. Then I'll go to my next pair. -1 subtract -3. This is actually -1 plus 3, which is also 2. Then we'll do -3 subtract -5. So I'm always doing bottom subtract top. And I get +2. And finally, -5 subtract -7. Again, +2. All of those first differences are the same. This second difference column is kind of useless. So this relation is linear. And the first differences are constant. And our equation is in the form y equals mx plus b. Plus we have a line on our graph. So 3 forms of proof or evidence that the relation is linear from the equation, from the first differences, and from the actual visual itself. Now, let's move on from linear and let's do a quadratic example. So if I look at y equals x squared minus 2, first of all, I'm already thinking this is quadratic because I see that x squared term. So let's go ahead and practice a table of values when a quadratic is involved. So here I have an x in a single spot, but it is raised to the power of 2. So I'm going to do -2 all squared subtract 2. Well, thinking of BEDMAS, exponents come first. -2 squared just means -2 times itself. Well, that's 4. And 4 minus 2 is 2. So I'm going to plot that point. When x equals -2, y equals 2. So there it is. Let's try the next one. So now instead of x squared, I'm going to write -1 squared, subtract 2. Make sure if you're putting this into your calculator, you put the -1 in brackets just like we wrote it. So -1 all squared is +1, and 1 minus 2 is -1. So at -1, we're at -1. Next we have 0 squared instead of x squared, subtract 2. 0 squared is 0. And when I subtract 2, I'm at -2. So 0, -2 is our next coordinate. Then I write 1 squared, subtract 2. 1 squared is 1. And when I subtract 2, I get -1. So now I'm seeing a repetition in one of the y coordinates. So when x equals 1, y equals -1. So I'm seeing it curve back upwards. And finally, instead of x squared, I'm going to write 2 squared, subtract 2. So 2 squared is 4, and 4 subtract 2 is 2. So 2, 2 is my next coordinate. And I will connect my dots and put arrows at the ends of my parabola. So I have already two forms of proof that this is quadratic. I see a parabola on my graph, and I see an x squared in my equation. Now there's one more form of proof that we're going to find, and we're going to calculate those first differences. So I'm going to go to the bottom of my table, I'm going to pair them up, and I'm going to do 2 subtract -1, and that gives me 3. Let's go to the next one. -1 subtract -2. That's actually -1 plus 2, which is +1. So these aren't matching, which I didn't think they would because I don't have a line on my graph. Next we have -2 subtract 1, which is actually -2 plus 1, so that's -1. And finally, -1 subtract 2, which is -3. So they're all different. Whenever your first differences are different, we want to go to our second differences. And all we're going to do, we're going to use these new values and we're going to pair them up. So I'm going to do 3 subtract 1, and I get 2. I do 1 subtract -1, I get 2. And -1 subtract -3, and I get 2 again. So when the second differences are constant, you get a quadratic relation. So this relation is quadratic. The second differences are constant, and it is in the form y equals ax squared plus bx plus c. So that is just the standard form for a quadratic. We are missing that bx part because there's no x term there. But the fact that you have an x squared, that tells you everything you need to know. So even if we look at our next one, y equals -2x squared minus 6x, I know it's going to be a parabola, and I know it's quadratic because of that x squared term. So let's try this table of values, and then we'll do a little summary of linear versus quadratic. Okay, so in this example, we do have an x in 2 places in our equation, so we're going to have to substitute the x value twice. So I have -2, and then instead of x, I'm going to write -4 squared, subtract 6 times -4. Now you can plug this into your calculator to get your answer, but I'm going to do this with BEDMAS. So with BEDMAS, the exponents come first. So -4 squared is 16. So that's all I'm going to clean up right now. Now, it is going to be a little bit squished. I'm going to go up here. I'm going to do my multiplication. So -2 times 16 is -32, and -6 times -4 is +24. And this gives me -8. So when x is equal to -4, y is equal to -8. And this is my coordinate here. Now let's try the next one. And if the table is too small for you, you can do it on a separate piece of paper as well. And the reason it's so small is because you don't actually have to do BEDMAS to get your value. I do expect to see that first line. Okay. So -3 squared is 9. So all I did this portion. And then the rest I'm going to rewrite. And then -2 times 9 is -18. And -6 times -3 is +18. So that gives me 0 when I add -18 plus 18. So when x equals -3, y equals 0. Okay, the next one. -2 times -2 squared minus 6 times -2. So I'm just replacing the x in -2x squared minus 6x. And then first step is always your exponents. So -2 squared is +4. So that's the only thing I'm changing. The rest I am just rewriting. But now I'll do the multiplication because that comes next in BEDMAS. So -2 times 4 is -8. And -6 times -2 is +12. And when I add -8 and 12, I get +4. So when x equals -2, y equals 4. Next one If you would like, you can pause the video here just to see if you can do the bed mass on your own, or you can just go to your calculator and plug it in to make sure you get the same answer that I do. I'm going to continue with the bed mass though. So -1 squared is +1. So -2 times 1 is -2, and -6 times -1 is +6, and that gives me 4 as well. So at -1, we're still at 4, and then -2 times 0 squared, subtract 6 times 0. Well, 0 times anything is 0, so everything's going to disappear, and you'll see that in a second. So 0 squared is 0. And then if I do -2 times 0 or -6 times 0, it's just 0. So that's always a good one to do in your table. And finally, x equals 1. So I have -2 times 1 squared instead of x squared, and then -6 times 1 instead of -6x. 1 squared is 1. When I do my multiplication, -2 times 1 is -2, and -6 times 1 is -6. And together, that gives us -8. Okay, when I connect my dots, I do think that I'm gonna have a vertex somewhere here. I don't know what it is exactly, but I'm not just gonna go across like a little square. So I'm gonna add a little, curve to it. And there we are. There's our parabola. So if I look at the graph, I can see it's a parabola. If I look at the equation, I see the x squared as my hint that it is quadratic. And the other proof is going to be those second differences. So let's go ahead and start with the first differences. We're going to start with the bottom ones. So the -8 subtract 0. Then the 0 with the 4. So 0 minus 4 is -4. They're different, which is expected, but it's okay here. The 4 with the 4, so 4 minus 4 is 0. Then the 4 with the 0, 4 minus 0 is 4. Then the 0 with the -8, be careful with your double negative here. 0 minus -8 is +8. They're different, that was expected. So now we take up our first differences, we pair them up, and we subtract. So -8 subtract -4 is -4. -4 subtract 0 is -4. 0 subtract 4 is -4. And 4 subtract 8 is -4. So they all match, which is your third piece of evidence that this is quadratic. So the second differences are different, or the second differences are constant, and it is in the form y equals ax squared plus bx plus c. So in terms of your comparison of linear versus quadratic, linear, the graph is just a line, either going up or going down. The quadratic, you have a parabola that's opening up or opening down. In terms of the equation, y equals mx plus b for the linear. And then I'm just going to write, well, I'll write the standard equation here, but I'm just going to make a note, the key part is the x squared. The other parts might be missing. You might be missing the constant, you might be missing the x, but it's okay. Which differences are constant? For the linear, it's the first differences. For the quadratic, it's the second. Now there's one more little thing that I want to look at, and it's about the parabola opening up or down from the general equation. So I'm going to go back up for a second. And if you look at the previous example, we had y equals -2x squared subtract 6x, and our parabola opened down. If you look at the one above, we had y equals x squared subtract 2, and our parabola opens up. Now, the differentiating feature that does this is the coefficient of x squared. In front of x squared here, it's a +1. Here, it's a -2. So when the coefficient of x squared is positive, your parabola is going to open up. When it's negative, your parabola is going to open down. So I'm just going to write that. And the coefficient of x squared is a. So the parabola opens up when a is positive, and it opens down when a is negative. And that's it. Quite a few parabola properties here. So when you see a parabola, you should be able to identify your vertex, the optimal value, the axis of symmetry, the x-intercepts, and the y-intercepts. You should also be able to take an equation and create a table of values for your parabola so that you can graph it. And that's it for our parabola properties.